Welcome to Artificial Intelligence, a modern approach. In this video, we embark on a journey through the world of AI, exploring its history, foundational concepts, and the key ideas that have shaped the field. We'll discuss what makes AI such a compelling area of study, why it's considered one of the most exciting frontiers in science and engineering, and how it has evolved over the decades. Whether you're a student, a professional, or simply curious about AI, this video will provide a comprehensive overview, setting the stage for deeper exploration into intelligent agents, reasoning, learning, and more. Artificial intelligence, or AI, is a field that seeks not only to understand intelligence but also to create intelligent entities. But what exactly is AI? Definitions vary, ranging from systems that think like humans to those that act rationally. Some focus on mimicking human thought processes, while others emphasize achieving the best possible outcomes, regardless of whether the approach is human-like. Throughout history, researchers have debated whether AI should aim to replicate human behavior or strive for ideal rationality. In this video, we'll explore these perspectives and see how they influence the design and goals of AI systems. AI can be categorized along two main dimensions: whether it focuses on thought processes or behavior, and whether it aims to match human performance or achieve ideal rationality. This gives us four approaches: thinking humanly, thinking rationally, acting humanly, and acting rationally. Each approach has its own methods and goals. For example, the Turing test emphasizes acting humanly, while logic-based systems focus on thinking rationally. Understanding these approaches helps clarify the diverse research directions within AI and why different subfields prioritize different objectives. The Turing test, proposed by Alan Turing in 1950, remains a landmark in defining machine intelligence. To pass the test, a computer must convincingly imitate human responses in conversation, requiring capabilities in natural language processing, knowledge representation, automated reasoning, and machine learning. The total Turing test extends this to include perception and robotics. These disciplines, language, reasoning, learning, vision, and robotics, form the core of AI research. While few researchers focus solely on passing the Turing test, its requirements continue to shape the field's development. Thinking humanly involves modeling the actual processes of human thought. Cognitive science combines AI with psychology and neuroscience to build computer models that simulate human reasoning and problem solving. By comparing the behavior of these models with human subjects, researchers gain insights into both artificial and natural intelligence. This approach has led to advances in areas like computer vision and natural language understanding, where understanding human cognition informs the design of intelligent systems. The thinking rationally approach to AI is rooted in logic and mathematics. Dating back to Aristotle, this tradition seeks to formalize correct reasoning processes. Logical agents use formal systems to draw valid conclusions from given premises. While logic provides a powerful framework, it also presents challenges, such as representing uncertain knowledge and managing computational complexity. Despite these obstacles, logic remains a foundational tool in AI, especially for knowledge representation and automated reasoning. The rational agent approach defines AI as the study of agents that act to achieve the best possible outcome, given their knowledge and percepts. Rational agents operate autonomously, perceive their environment, adapt to changes, and pursue goals. This approach is more general than logic-based reasoning, encompassing a variety of mechanisms for achieving rationality. It also provides a mathematically precise standard for evaluating intelligent behavior, making it a central concept in modern AI. AI draws on a rich philosophical tradition, with roots in questions about the nature of mind, reasoning, and knowledge. Philosophers like Aristotle, Descartes, and Hobbes explored ideas about logic, dualism, and materialism. The debate over rationalism versus empiricism and the development of logical positivism laid the groundwork for thinking about intelligence as a computational process. These philosophical foundations continue to influence how AI researchers conceptualize knowledge, reasoning, and action. Mathematics has provided essential tools for AI, including formal logic, algorithms, and probability theory. Boolean logic, first-order logic, and the theory of computation define what can be computed and how. Concepts like tractability and NP-completeness help identify which problems are feasible for intelligent agents. Probability theory, pioneered by figures like Pascal and Bayes, enables reasoning under uncertainty, a critical aspect of real-world AI systems. Economics has contributed decision theory and game theory to AI, providing frameworks for making rational choices under uncertainty and in multi-agent settings. Concepts like utility, expected value, and Markov decision processes guide the design of agents that seek to maximize their performance. These ideas are especially relevant in areas like automated planning, resource allocation, and strategic interaction among intelligent agents. Neuroscience studies how the brain processes information, offering inspiration for AI models. The structure and function of neurons, the organization of the cerebral cortex, and the mechanisms of learning in the brain have all influenced the development of artificial neural networks. While computers and brains differ in many ways, understanding biological intelligence provides valuable insights for building intelligent machines. Psychology, especially cognitive psychology, views humans and animals as information processing systems. Experiments on perception, memory, and problem-solving inform AI models of cognition. The field of cognitive science bridges AI and psychology, using computer simulations to test theories of human thought. This interdisciplinary approach has led to advances in understanding both natural and artificial intelligence. The development of digital computers has been essential for AI. From early electromechanical machines to modern supercomputers, advances in hardware have enabled increasingly complex AI applications. Innovations in software, programming languages, and operating systems have also played a crucial role. AI research has in turn contributed to computer science, introducing concepts like time sharing, interactive interpreters, and object-oriented programming. Control theory and cybernetics study how systems can regulate their behavior through feedback. Early self-controlling machines like water clocks and thermostats laid the groundwork for thinking about autonomous agents. Norbert Wiener's work on cybernetics connected biological and mechanical control systems, influencing the development of AI. Modern control theory focuses on designing systems that maximize objectives over time, paralleling the goals of intelligent agents. Linguistics explores how language relates to thought, providing insights for natural language processing in AI. Noam Chomsky's theories challenged behaviorist views, emphasizing the creativity and structure of language. AI and computational linguistics have grown together, tackling the complexities of understanding and generating human language. Robust language understanding requires not just syntax, but also knowledge of context and meaning. AI as a formal field began in 1956 at the Dartmouth Workshop, where researchers like John McCarthy, Marvin Minsky, and Alan Newell gathered to explore the possibility of simulating intelligence with machines. Early successes included programs that could prove mathematical theorems and play games like checkers. These pioneering efforts set the stage for decades of research, innovation, and debate about the nature and potential of artificial intelligence. The early years of AI were marked by optimism and rapid progress. Programs like the General Problem Solver and the Geometry Theorem Prover demonstrated the potential of symbolic reasoning. However, as researchers tackled more complex problems, they encountered significant challenges, including the limitations of computational resources and the difficulty of scaling up simple solutions to real-world tasks. These challenges led to a more nuanced understanding of what AI could achieve. As AI matured, researchers realized that general-purpose search methods were insufficient for complex tasks. The development of knowledge-based systems, such as DNDRAL and MYCIN, demonstrated the power of domain-specific expertise. These systems used large sets of rules and specialized knowledge to solve problems in areas like chemistry and medicine, paving the way for the expert systems that would later become commercially successful. By the 1980s, AI had moved from academic research to commercial applications. Expert systems were deployed in industries ranging from manufacturing to medicine, saving companies millions of dollars. National initiatives like Japan's Fifth Generation Project and the U.S. Microelectronics and Computer Technology Corporation aimed to advance AI technology. However, the field also experienced setbacks, including the AI winter, when expectations outpaced results and funding declined. In the mid-1980s, neural networks experienced a resurgence with the rediscovery of the backpropagation learning algorithm. Connectionist models offered new ways to approach learning and pattern recognition, complementing symbolic and logic-based methods. This period saw advances in both the mathematical understanding of neural networks and their application to real-world problems, leading to the modern era of deep learning. Recent decades have seen AI adopt more rigorous scientific methodologies. Researchers now emphasize building on existing theories, conducting controlled experiments, and using statistical analysis to validate results. Shared datasets and benchmarks enable reproducibility and fair comparison of approaches. This shift has led to steady progress in areas like speech recognition, machine translation, and data mining, with AI systems achieving robust, real-world performance. The concept of the intelligent agent has become central to AI. Agents are systems that perceive their environment and act to achieve goals. This perspective unifies diverse AI subfields and emphasizes the importance of autonomy, adaptability, and goal-directed behavior. Intelligent agents are now found in applications ranging from web search and recommendation systems to robotics and autonomous vehicles. The availability of massive datasets has transformed AI research and applications. With billions of words, images, and other data sources, learning algorithms can achieve remarkable performance, sometimes surpassing the impact of algorithmic improvements. Techniques like unsupervised learning and data-driven pattern recognition have enabled breakthroughs in natural language processing, computer vision, and beyond. Today, AI powers a wide range of applications. Robotic vehicles navigate challenging environments, speech recognition systems enable natural conversations, and planning algorithms control spacecraft millions of miles from Earth. AI systems play games at superhuman levels, fight spam, optimize logistics, and translate languages. These achievements are the result of decades of research, integration of diverse techniques, and the relentless pursuit of intelligent behavior. The book Artificial Intelligence, A Modern Approach is organized into 7 parts, covering topics from intelligent agents and problem-solving to knowledge representation, reasoning under uncertainty, learning, perception, and robotics. Each chapter builds on foundational concepts, providing both theoretical insights and practical algorithms. The book serves as a comprehensive guide for students and practitioners alike. At the heart of AI is the concept of the intelligent agent. An agent perceives its environment through sensors and acts upon it through actuators. The agent's behavior is determined by an agent function, which maps percept sequences to actions. Designing intelligent agents involves specifying their performance measures, knowledge, actions, and perceptual capabilities. This framework applies to everything from simple vacuum cleaners to autonomous vehicles. A rational agent is one that does the right thing, maximizing its performance measure based on its percepts and knowledge. Performance measures must be carefully designed to reflect the true goals of the agent, avoiding unintended behaviors. Rationality depends on the agent's knowledge, available actions, and percept history, not on omniscience or perfection. This distinction is crucial for building practical AI systems. Intelligent agents must be able to learn from experience and adapt to new situations. Autonomy refers to the agent's ability to improve its behavior based on its own percepts, rather than relying solely on prior knowledge from its designer. Learning enables agents to handle uncertainty, explore unknown environments, and refine their strategies over time, making them robust and flexible in dynamic settings. Designing intelligent agents begins with specifying the task environment using the PEAS framework: performance measure, environment, actuators, and sensors. This structured approach ensures that all relevant aspects of the agent's operation are considered, from the goals it must achieve to the actions it can take and the information it can perceive. The PEAS framework is applicable to a wide range of agents, from taxi drivers to web crawlers. Task environments can be categorized along several dimensions, such as observability, determinism, episodic versus sequential nature, static versus dynamic, and discrete versus continuous. These properties influence the design of agent programs and the choice of algorithms. Understanding the nature of the environment is essential for building effective and efficient intelligent agents. The vacuum cleaner world is a classic example used to illustrate agent design. In this environment, the agent perceives its location and whether the square is dirty, and can choose actions like moving left or right and cleaning. By analyzing different agent functions and performance measures, we can explore the concepts of rationality, autonomy, and learning in a controlled setting. While simple environments like the vacuum world help illustrate basic concepts, real-world agents operate in far more complex settings. Automated taxi drivers, for example, must navigate unpredictable roads, interact with passengers, and handle a wide range of sensory inputs. Designing agents for such environments requires careful consideration of sensors, actuators, knowledge representation, and decision-making strategies. Not all intelligent agents operate in the physical world. Software agents, or softbots, interact with digital environments like the internet. These agents perform tasks such as information retrieval, recommendation, and automated negotiation. The complexity of digital environments rivals that of the physical world, requiring sophisticated algorithms for perception, reasoning, and learning. Environments can be fully or partially observable, deterministic or stochastic, episodic or sequential, static or dynamic, and discrete or continuous. Each dimension presents unique challenges for agent design. For example, partially observable and stochastic environments require agents to reason under uncertainty and update their beliefs based on new information. Agent architectures define how agents process percepts and select actions. Simple reflex agents respond directly to percepts, while model-based agents maintain an internal state. Goal-based agents plan actions to achieve specific objectives, and utility-based agents evaluate the desirability of outcomes. The choice of architecture depends on the complexity of the environment and the agent's capabilities. Knowledge representation is a cornerstone of AI, enabling agents to reason about the world, draw inferences, and make decisions. Different types of representations, atomic, factored, and structured, offer varying levels of expressiveness and efficiency. Choosing the right representation is crucial for building intelligent agents that can handle complex tasks. Many real-world environments are partially observable and non-deterministic. Agents must estimate the state of the world, update their beliefs, and plan contingently for different possible scenarios. Techniques like probabilistic reasoning, belief state maintenance, and hierarchical planning help agents navigate uncertainty and achieve their goals. Machine learning has become a central focus of AI, with new algorithms enabling agents to learn from data, adapt to changing environments, and improve over time. The latest approaches include deep learning, ensemble methods, and learning from very large datasets. These advances have led to significant improvements in areas like computer vision, speech recognition, and natural language processing. As AI systems become more capable, the boundaries between subfields like robotics, vision, and language processing are blurring. Modern intelligent agents integrate multiple capabilities, combining perception, reasoning, learning, and action to achieve complex goals. This holistic approach reflects the interconnected nature of intelligence, both artificial and natural. AI has achieved remarkable successes in recent years. From autonomous vehicles and game-playing champions to language translation and logistics optimization, intelligent systems are now embedded in many aspects of daily life. These achievements are the result of advances in algorithms, data availability, and computational power, as well as the integration of diverse AI techniques. Despite significant progress, AI still faces many challenges. Achieving human-level intelligence, ensuring ethical and safe behavior, and building systems that can generalize across tasks remain open problems. Researchers continue to explore new approaches, drawing on insights from philosophy, neuroscience, and other disciplines. The future of AI promises both exciting opportunities and important responsibilities. AI research is supported by a vibrant scientific community, with conferences, journals, and professional societies dedicated to advancing the field. Collaboration and open sharing of ideas, data, and code have accelerated progress and fostered innovation. As AI continues to evolve, the community remains committed to rigorous experimentation, peer review, and the responsible development of intelligent systems. To deepen your understanding of AI, consider exploring the exercises and projects suggested in the book. These range from defining key concepts and analyzing classic papers to investigating the capabilities of current AI systems. Engaging with these challenges will help solidify your grasp of the material and inspire further inquiry into the fascinating world of artificial intelligence. In this video, we've explored the foundations, history, and core concepts of artificial intelligence. From philosophical debates to practical applications, AI encompasses a rich tapestry of ideas and techniques. The journey from early symbolic reasoning to modern data-driven learning highlights both the challenges and the promise of building intelligent agents. As the field continues to evolve, understanding these fundamentals will be essential for anyone seeking to contribute to or benefit from AI. As we conclude, it's clear that artificial intelligence is both a scientific and engineering discipline with profound implications for society. The integration of learning, reasoning, perception, and action continues to push the boundaries of what machines can achieve. By building on a solid understanding of AI's foundations, we can look forward to a future where intelligent agents enhance our lives, solve complex problems, and open new frontiers of discovery.